Today's virtual lecture is going to be just quickly going through and implementing in PyTorch the nonlinear solve that we've been talking about how to do. So we've already been playing a little bit in the last homework assignment with how to learn a constant coefficient stencil, right? And that's enough to approximate some linear operators. But now if we want to be able to capture an arbitrary nonlinear operator, right, we want a neural network. Instead of just learning constant coefficients or a stencil, we're going to have something where the stencil will evolve nonlinearly as a function of the grid function values, right? The nodal values of the solution at each time step. Okay, so let's dig into it. I put together a Jupyter notebook that you can find through the link on the course GitHub, and you can step through it. Okay, so if you open up the Jupyter notebook, you'll see it here. What I'm going to do today is just step through the logic for how to put this together. There's a lot of moving parts, so I'm just going to go through this very slowly, and also in a way that hopefully you can use as kind of a cookbook, right? So in general, if you want to make a machine learnable PDE solver, right, first take a very simple NumPy implementation of the solver. Make sure that without machine learning, you know how to do it, right? How to correctly put the method together. Then the next step is that you put it into PyTorch, and then you replace parts of the solver with corresponding machine learnable parts. Okay, so to get started, you can see that I took the code from the previous homework assignment and just copied and pasted it in here into this block. And what it consists of in this finite difference operator class is just this trainable, as of right now, trainable constant coefficient parameters for the stencil weights. And so when you apply a forward pass of the finite difference operator, it loops over all of the nodes, loops over the neighbors of those nodes, and then does some indexing to take care of periodic boundary conditions, and then evaluates the stencil. Okay. So the first thing that we're going to do, we're just going to change the syntax slightly. So this block of code functions identically. Okay. But the forward pass, I'm just changing the syntax a little bit because this is going to make it easier to interact with neural networks down the road. Okay, so here, the exact same thing. We loop over all the nodes. Now what I've done is I've used list comprehension to identify for node I the list of indices for neighbors, n left neighbors to the left and n right neighbors to the right, but in such a way that it respects the periodic boundary conditions. Okay, so if after evaluating this list comprehension, if you hopefully everybody's at this level of Python, but if you give an array a list of indices, right, it'll return the corresponding entries of the array at those indices, right? So doing this, we can pull out the grid function values of the neighbors. Okay, so then applying the finite difference stencil is as simple as doing this torch.sum, and now it's the product of the stencil with the corresponding values. Okay. Okay, now that we have this stood up, our next goal is going to be to put in a nonlinearity. Right? And as we talked about in class, we discussed how we can show that a nonlinear system of equations, when does it have a solution or not? And we considered this simple setting where you have a perturbation, right? So you have an invertible matrix A, and then we have a small nonlinearity. So this epsilon is a parameter that's less than 1, and it's meant to suggest that this nonlinearity is small relative to the magnitude of A. So what we had showed in class with the analysis is that if you assume that n is Lipschitz, then you can prove that this this problem has a unique solution as long as the matrix norm of A inverse is large relative to the Lipschitz constant of n. Right, so that's a bit mathematically technical, but all it's saying is, you want that first term to be big relative to the nonlinear term. Okay, so what we're going to do here, motivated by that, is we're going to have a diffusion stencil for A hard-coded into the method. Right? And basically what that's going to be doing is it's exactly like artificial viscosity that we've talked about before, and our hope is that this viscosity is going to be able to help us control the nonlinearity that the neural network is going to pick up. Okay, so what we're going to do, we're going to replace that matrix A with this this diffusion stencil, which is the composition of the forward and backward difference in order to get a second order derivative. And this has some nice properties in a periodic domain. Later on in the class we'll talk about these kind of things, but you can actually prove all sorts of stuff about this, that it's invertible and various nice properties that it has. But for now, I'm just going to ask you to take my word for it. Right? We're just going to assume that this is a nice invertible matrix. And for today, we're just going to talk about the plumbing of how do you write this code. Okay. So what we're going to do first, we want to hard code this this diffusion term in. What we're going to do is we're going to have a trainable magnitude for the diffusion. So we're introducing a new parameter that the model is going to train. And it has to be positive, right? So if you have negative diffusion, then your model will definitely not be stable. That's the opposite of stability. Just instantly explode. So we need to make sure that the coefficient in front of this diffusion term is positive. So in order to enforce that, we are going to actually train the log of that magnitude, and then if we exponentiate that, then we'll get then we'll have something guaranteed to be positive. Okay, so that's how we introduce that one parameter here. We initialize it to have a value of 0 to start, or e to the 0 is equal to 1, right? So that means the stabilizing parameter is 1 at the beginning of training. Okay, and now down here you can see exactly where we hard code this diffusion operator, the usual stuff. We have to be careful using the modulus in order to enforce the periodic boundary conditions. And you can see that when we evaluate our stencil, that all we've needed to do is tack this little piece on. Okay, so that's fine. So now we've shown how to add a hard-coded diffusion to the trainable stencil. The next thing we're going to do is add the neural network. So again, I'm assuming in this class that folks have some experience, maybe not in PyTorch, maybe TensorFlow, maybe MATLAB, whatever, but that people have messed around with neural networks a bit before. We'll talk more about this later, but for now, I'm just going to take a relatively out-of-the-box nonlinear network. Right, so you can see in terms of the initializer for the class, now I've added the following. We're going to put in a nonlinear network. So a this multi-layer perceptron or dense neural network is going to consist of a linear layer that will map from the number of nodes in the stencil up to a hidden dimension that's presumably going to be larger, and that's just like a hyperparameter that we'll play with. Then we'll have a bunch of nonlinear layers that alternate between affine transformations, right, like multiplication by weights and addition by biases, and then a nonlinear activation function, and then we'll do that operation over and over and over again. And that's so this is, people talk about deep learning. This is maybe the simplest example of how you do that. Then at the final layer, we have another linear layer which takes us back down to from the dimension of the latent space down to a dimension equal to the number of stencil points. Okay, so there's some small details about how we want to put this together that I'll step through a bit slowly. All right, so first, just some syntax for folks who haven't seen this before. What we're going to do is we're going to create a list with all of the layers, and we'll just append these layers on one at a time. Okay, so to get started with, we have a linear layer. I want to highlight, just jump around. I want to highlight that everything that we're going to do in this class is going to be in double precision. So make sure that you track that. That's because scientific computing, we just need much more accuracy than people typically use in computer vision or natural language processing. So all of the defaults for all machine learning libraries are to work in float 32 or single precision. So just make sure you're being careful with that. First of all, we add this linear layer. As far as activation functions go, we're going to be using tanh activations. That's because we want our nonlinearity to be Lipschitz. So if you had, basically just think that discontinuities are bad. We want a nice smooth activation function. So that's why we're reaching for a tanh here. Then here are hidden layers. The parameter num layers will choose how many of these we have. This hidden dim param will choose the width, right? So those two parameters specify the depth and the width of the network, and they're passed up here in the constructor argument. And then finally, there is an issue with standard multi-layer perceptrons, which is that they have what's called the exploding vanishing gradient problem. So one trick that I'm just going to say in a hand wavy way for now is that you add skip connections or to build what's called a residual network. So that's what this piece is doing, right? And all it says is instead of saying that layer m+1 is equal to an activation of a weight times x n, instead we say xm+1 is equal to xn plus a nonlinear activation of a weight times xn. Okay, so we just add this identity piece. Okay, so this class provides a means to do that. So basically the way this is functioning is we have all of the MLPs without the skip connections in this hidden layers list. And then we use this list comprehension right here to add skip connections to each one of those blocks. Okay, and then this line converts those into a sequential neural network. Okay, so you can view this just as kind of a off-the-shelf implementation of a residual layer, right? And so then we tack that onto our list of all of our building blocks, this layers list. And then finally we add an output layer, right, which is just going to be this linear layer that goes from the hidden dimension down to the number of stencil points that we need. There's one final trick that we're going to talk about here, which is that we initialize the weights and biases of this linear layer to 0. So what that means is that at the beginning of training, the nonlinearity maps to 0. So for the first step of training, we'll just have the hard-coded diffusion with no nonlinear contribution. We'll see for certain problems that this is very helpful because depending on the scheme that you're choosing, if you need a good if you initialize your network so that it's too nonlinear, it won't be able to train. Okay, so this is just a little trick where we can kind of do a warm start where we begin with no nonlinearity and then we let it gradually fill in or rise up. Okay, and now when we pass this unrolled list, so star layers means take each of the arguments in this list and pass it as parameters to the constructor of this nn.sequential class, right? And now this thing is a neural network. Okay, so again, if you're new to machine learning, if this felt tricky, it's basically just syntax. But I'd encourage you to drop by the office hours if you want to talk a bit more about this. But I'm assuming that this should be relatively clear to most people taking the class. Okay, so now we're back to our forward pass, right? And now all we're doing is we take this stencil, exactly the same as before, and now we feed that stencil to the neural network, right? And we collect the output here. And we view this nonlinear stencil. We apply it, I've commented out what was there before. This is what's here now. And all I've done is I've swapped out that constant coefficient stencil with the output of the neural network. Okay, so let's run this. Here is a case. So what I'm going to do is I'm going to try to train a model so that we give it an example of a single time step. Right, so as data, we consider a single Fourier mode, sine k times x. And we're going to train it so that it exactly recovers the solution to the transport equation. Okay, so if we apply an explicit Euler update, this will take us from the initial condition to the mode shifted over by delta t. Okay, so it's going to reverse engineer a stencil that accomplishes that. So now you can see how we're building this up, right? So first we've initialized our model. We're saying this is a 3-point stencil, so one neighbor to the left, one neighbor to the right. Depth 2, width 25 network. Don't worry too much about how to choose those. There's no good way to know how. I just messed around with some different choices. I'm trying to come up with a neural network that is as small and simple as possible. So I came to these by basically just making a random guess and then dialing them back to smaller models until the code stopped working. All right, so now that we've done that, here's our training loop. Standard PyTorch stuff. We're gonna, on each step, we're gonna zero out the gradients. We're going to generate the data label pair. Right, so we know what the initial condition is, and then we have an example or a label which says what the update should look like for that. There's one small trick that I'm going to do here to prevent overfitting, where I'm just going to add a small amount of noise to that example at every time step. there's lots of ways to prevent overfitting and so on. This is just a quick and dirty one. You don't need to overthink it. Right, and so we evaluate our model applied to this initial condition, and then we define a loss, which says how far our learned time stepper is compared to the true one that that we're supervising it or we're steering it with. And then we do loss dot backward in order to take a atom optimizer step. Okay, so I'm going to start that training, and it's not super slow without a GPU, but it will take a few minutes. So I'm gonna pause the video and hop back on once it's finished training. Okay, so now you can see I let it train for 5,000 epochs. Remember that there's 1% noise, and we're looking at the mean square loss. The square of 0.01 is 10 to the minus 4. And basically that means the loss is never going to get below 10 to the minus 4 because we're always adding that magnitude of noise on top. And you can see that pretty quickly it'll converge around there. I let it train for a while. That way the noise can serve to regularize it and keep it from overfitting. So that should be a standard trick, right? The idea of generalization and overfitting and tricks to mitigate that. That's something that we cover in 531. But again, if this is something that's new to you, just come by office hours. I'm happy to fill in the gaps. Okay, so now we have a trained model. And so what I'm going to do is take the initial condition and then solve the trained model. I'm just going to take 20 time steps. So when I do that, what we see is, and 20 is the exact right number. We see that for the first few time steps, it's absolutely beautiful. Right? You can see that it is, the wave is traveling from left to right. The magnitude is good. It's not growing or decaying. And then all of a sudden, bam, an instability appears. And if you run this for one more time step, you can see that single instability mode is growing exponentially. Okay, so now here's two more steps. Right, it's a magnitude 20. Take another step. Magnitude 700. One more step. So on. It's going and going. So what's happening is we have a numerically unstable mode here, right? So we've identified a time stepper, which is good from an accuracy point of view, but is terrible from a numerical stability point of view. And so what's happening is that even though we have a good fit to the data, we have an unstable eigenmode in this. Basically there's, even though there's a very small error, it'll grow exponentially until it, in the eyeball norm, seems to just all of a sudden appear in this 20th time step as this blue line, right? And you can't even see it in the time step prior to that. Right here, you have some very small wiggles, right? And if you go back a few steps, you wouldn't even know, right? So right. So what are we gonna do? The final trick that I'm gonna go through today is a factor of the polynomial reproduction stuff that we've talked about. Okay, so we know that for a method to be consistent, it has to have this polynomial reproduction property, and that's enough to enforce consistency. what we are going to do here is we're going to enforce the property that the sum of the stencil coefficients should be equal to 0, right? It's a derivative operator, so if you apply this thing to a constant field, it should return 0, even if it's doing all sorts of other crazy stuff. Okay, so the way we're going to do that, the constructor doesn't need any changes to it. We're going to do this interesting trick where it's just this single line, but we take the output of the neural network and, right, so this is outputting the stencil coefficients. And I'm going to remove the last stencil coefficient, right? This -1 means grab that final stencil coefficient, and I'm going to replace it with the net with minus the sum of all of the other stencil coefficients. Okay, so because I've overwritten this in this way, now when I sum over the stencil, it's equal to 0, exactly to machine precision. Okay, so this is the only change I've made to the code. Just that minor change. Now I'm going to run it. And let it go. I'm going to pause the recording. I'm going to come back in a few minutes when training has stopped. Okay, so we can see that it's just finished recording. Same as before, we have this 1% noise that we're adding on. So you can see it pretty quickly bottoms out at a loss of 10 to the -4, roughly what we're expecting. So now I'm going to do the same thing. I'm going to run our learned solution, and we can see that it looks quite nice. Okay, so this is 20 steps. That's exactly when it started to fail previously. I'm going to run it for 40 steps, twice as long. Still no issue. I'm going to run it for 100. Looks good. Run it for 1,000. And it takes a little while. Thinking. And I can see why it took so long to think, because that's a lot of plots that's making right on top of each other. You can see it though that they are all the exact right magnitude. And now I'm only going to print every 100 steps, but it should still look good. Okay, so what we've seen now is that we have this nonlinear stencil that can pick up. Without this condition, we are I'm not sure what to think about that plot. It's distracting me. And put it away. Without that condition, that polynomial reproduction condition, we got something that had good accuracy, but was numerically unstable. Now that we've put this condition back in, we've learned a stencil, it matches the data, and it's stable for long time integration. Not only is it stable though, right, we can see that it's doing what we want, meaning there is no numerical instability where errors compound and the amplitude grows over time. It's also, there's minimal numerical dissipation, so it's not overdamped and the amplitude would decay in that case, right? So this is exactly what we want. And so in the lecture after this one, basically what we're going to get into is how to do the numerical analysis for this to actually understand why this works. At this point, what you have now is a complete PD discovery code that you can use to fit models to 1D data. So hopefully that was clear. I want to say again, if folks want some help, I'm going to hold some extra office hours on Tuesday. I'm anticipating that this will either have been very straightforward for you if you already know PyTorch well, but if this is your first time doing PyTorch, this could be challenging, and it's a bit more intensive than just doing some like off the shelf model and running it. So yeah, come by office hours tomorrow. I'll be in a little bit late because of my son's daycare, but I will be in there basically all day starting maybe like 10 to 1, 10 to 2. So just shoot me an email if you want to drop by, and yeah, thanks.